Hi, in this video, we want to take a look at the gamma distribution. Okay, so the gamma distribution is a continuous distribution, and all the possible values are greater than or equal to 0, or just greater than 0, depending on how you want to articulate it. Now, something that's funny about the gamma distribution is it has two presentations. All right, so the one version has a shape and scale parameter. The other one has a shape and rate parameters. Okay, so if we look at the shape and scale parameterization, we see that we have 1 over the gamma function of alpha, theta to the power of alpha, x to the power of alpha minus 1, and then we have an exponential of e to the negative x divided by theta. So x is a positive real number. Alpha is called the shape. Theta, which is greater than 0, is called the scale. Our expected value is going to be alpha times theta, and our variance is alpha times theta squared. Okay. Now, this version of the gamma distribution, this is most useful when the emphasis is about the expected value. So usually people prefer this one when they have a good idea of what the expected value is and they want to have like more of a direct connection between the value and the parameters. So this is very nice. My understanding is that this one is used quite often in economics. Now the other presentation, the other parameterization, is with the shape and the rate. All right, so here, alpha is greater than 0 is the shape, so that's nothing new. Beta greater than 0 is the rate. Now, the difference is where does beta appear in the equation, in the density? So here we have beta up top in the fraction, beta to the alpha. Then we have the gamma function of alpha, x to the alpha minus 1. Then we have e to the beta times x. So now here in this presentation, in the scale parameterization, we have x divided by the scale. And in the rate parameterization, we have x times beta in the exponential. Okay, well, when we do it this way, our expected value is alpha over beta, and our variance is alpha over beta squared. All right, so if we're dealing with an audience that's less comfortable with mathematics, then they're probably not going to be as comfortable with fractions, right? And so in that case, the rate parameterization is not the best one to work with. But a lot of mathematics works out easier with the rate parameterization and a lot of like the theoretical statistics side. So my personal preference on all the problems I've worked on in real life using the gamma distribution, I used the rate presentation, the rate parameterization. Now the two are equivalent. You can actually go back and forth between the two if you need to. You just need to know that the reciprocals, scale and rate, are reciprocals of each other. We just have to understand this and be ready to work with whichever one is presented to us. Now, something about this that we also need to be mindful of, if I'm reading a book, if I'm reading through an academic paper, if I'm using some software to work with the gamma distribution, well, I need to know which version is being presented to me, because my interpretation of what's going on will change depending on how the parameterization is going. So before this video, I looked at Wikipedia to review things, and there were some inconsistencies on how it presented what's going on. It actually bounced back and forth between scale and rate. So there, I have to use my knowledge of what's going on to make sure that I interpret it correctly. Now, the gamma function, so you'll notice that I have this gamma function of alpha in both versions of the gamma distribution. So this is where we get the name for the gamma distribution. It's from the gamma function. Well, what is the gamma function, you ask? Well, you're about to find out. All right, well, the gamma function, so if z is the variable, so this is important, z is the variable for this one, the function is equal to the integral from 0 to infinity of x to the z minus 1, e to the negative x, like that. And z is a positive number. All right, so now this defines a function. So something to check out about this is notice that we are integrating out the x. When I'm all done with this, there is no aspect of x at all in this. So it's just like your x leaves your life. Get it? Your x leaves you. All right, there we go. So now, this function, the gamma function, appears in a lot of parts of mathematics. It's very useful, very powerful. It's a special function. It has actually a bunch of special properties. We're going to look at just some, like 3 of the main ones. All right, so if I look at gamma of alpha plus 1, this is equal to alpha times gamma of alpha. All right, so what this does for us is if I know, if I need, let's say, gamma of 3.5, well, if I can figure out what gamma of 2.5 is, I can use a formula for that. If I can figure out what, to get that, I could use gamma of 1.5, and to get that, I could get gamma of 1/2. Okay. So now it works out also using this property and some, just regular calculations on the integral for the lower values of z, we can see that gamma of n plus 1, when we're talking about positive integers, is equal to n factorial. Well, that's nice. That makes calculations easy. And gamma of 1/2 is equal to the square root of pi. Isn't that interesting? All right. All right, so now something that is important in statistics is that we have probability distribution functions that we know are probability distribution functions. So every time I see particular functions, I know immediately that it is a PDF. And so what that does for me is that anytime in mathematics, if I see something proportional to that integral, and I'm integrating over the entire domain, I know the value that's going to end up being. So check this out. If I take the gamma distribution and I integrate from 0 to infinity, I know the value is going to be 1. Why? Because it's a probability distribution function. Okay, well, let's turn this on its head. If I look at this part of the formula of this, I realize that that's a constant value. When I'm doing integration, I can factor out a constant value. So I could potentially take this and factor that fraction out front. Okay. So now, what if I multiplied both sides by the reciprocal of that fraction? Well, the fraction would cancel out, right? So if I multiply both sides by the reciprocal of this fraction, then this part will disappear and I'll have the reciprocal on the right. So that tells me that anytime I integrate from 0 to infinity of x to an alpha minus 1 e to the negative beta x, it will always be equal to this. So why I like this is that anytime I see an integral that looks like this, I immediately use a formula. I'm not going to bother with calculus. I'm not going to do integration by parts. I'm just going to jump to the result I know that I'm going to get. That way I don't have to do any work. I'm very lazy. I'm always looking for the easiest way out. All right, so now let's go ahead and start thinking about expected values of random variables. All right, well, what we're going to do, we're going to use the special formula that we just established to figure out the expected value. Okay, so I want the expected value of x to the n. So this could be x to any power that is, and for this one, it has to just be a positive number for n. All right, well, that's going to be the integral by the definition of expected value. That's going to be the thing that I have inside here. I put here, and then I take my probability distribution function, and I integrate from 0 to infinity. Okay. Well, I notice that this is a constant number with respect to integration, so there's no x's floating around. So I'll go ahead and factor that out front. Now, I notice I've got x to the n. I have x to the alpha minus 1. So I know that I can just rewrite it that way. Okay. So now, here's the kicker. I look at this, and I go, wow, that looks a lot like something from that I've already seen, something from the gamma distribution. So I realized that if I was to take this formula up here and I replaced alpha with alpha plus n, I would get exactly this integral. So what I'm going to do in this formula up here, I'm going to replace alpha with alpha plus n, and that gives me this fraction here. All right, so now I'm going to simplify things. I see I've got beta to the alpha plus n. So I know alpha of them are going to cancel out. I'm left with beta to the n on the bottom. Now, here, these gammas don't directly cancel out yet. So, I've made it this far in my simplification. And I need to use that formula that we have where if I subtract by 1, I put out the value out front. And I'm going to go ahead and do that. Well, if I think about this, if I use this formula here, take the inside, subtract 1, move what you get out front, and reduce the inside by 1. Okay, well, I can do that, and I can keep on doing that over and over and over. I can do that repeatedly. So what I'm going to do is I'm going to apply that n times. So I'm going to subtract by 1 on the inside and pull out what I have after subtracting. Then I'm going to subtract by 1 again, pull the result out front to give me this. Subtract by 1 again, pull it out front. I keep on doing this over and over and over until I see that I get a gamma of alpha times all of these terms here. All right, so now as what I've made to this point, I know that the gammas cancel, and I'm left with this formula. Now in this presentation, it's not obvious why this is very nice. So we do have a nice formula, honestly, for any expected value of x to the n. So that's very good, but where is the utility? Why do we really care? It is a nice formula, but I'm not going to be doing the expected value of x to the 30th anytime soon. So, it's not that helpful. But what if I set n, let me scroll a bit. If I set n equal to 1, then I see that, all right, I start at alpha plus n minus 1. Well, n is 1, so then this part just cancels out to be alpha, and this formula goes all the way down until I reach alpha. So that means I start and end at alpha. Oh, sorry, this is the part I should be at. So the top is just alpha, and the bottom is just beta to the power of 1. Boom, I've got this. Now, when n is equal to 2, I plug in a 2 for here, and then 2 for here, and I see that I get alpha up top. Therefore, I stop, and I'm going to get alpha plus 1 and alpha, and then beta squared. So now I have expected value of x squared. Then I can compute the variance. So what I'm going to do for the variance, I'm going to use our familiar formula, and I'm just going to plug in these values that we've just computed. And so I take expected value of x squared. I subtract the expected value of x squared. I do some simplifications, and boom, we see that the variance is alpha over beta squared. So this is very nice. All right, the next thing to think about is the relationship between the exponential distribution and the gamma distribution. All right, so the exponential distribution is actually a gamma distribution with alpha equal to 1. Okay, so here, if I look at this, if I was to take a gamma distribution and I plugged in alpha equals 1, the x to the power of alpha minus 1 would cancel out because x to the power of 0 is 1. And then the beta term is left. And if I just simplify everything, I just get this value. Okay. So then, the expected value of x, everything follows the way that everything worked out previously. So this is very nice. Now, if I have a summation of gamma random variables, let's say that I have n independent gamma random variables, all with the same rate, but they can have different shapes. So they all have rate beta. They all have shape of alpha 1, alpha 2, alpha 3, alpha n. So these can be the same, these can be different. Then the sum of all of these gamma random variables will have, the summation itself will be a gamma random variable with rate beta, and the shape is going to be the sum of the shapes that we had for the individuals. All right. All right, so now, how could we use this dealing with time? Well, let's say that I'm waiting on some events. Let's say I'm interested in the 10th event. How long will it take for the 10th event to occur when the time between events is exponentially distributed with a beta rate? Well, then what I can do, I use this formula here for alpha equal, each of the alphas equal to 1. I see that I'll just get an n. And so I know that if I want the time to the nth event for independent, identically distributed exponential random variables, then the sum of time is going to be a gamma random variable with shape n and rate beta. Okay, so let's see if we can keep going with this. Well, so another neat aspect about this, and this comes from U substitution in calculus. If I apply this to our, if I apply this to a gamma random variable, is that if I have any gamma random variable with the shape and scale parameters, then C times X is also a gamma random variable. The shape is the same, but the scaling gets changed. Okay, well, how can we actually use this? Well, I know that the probability that X is less than or equal to a value given alpha, and let's say beta is equal to C, then this will be equal to the probability that X is less than or equal to C times X, where alpha is the same alpha value, beta is equal to 1. All right, so what this does, if I take a particular alpha value and I'm interested in maybe a range of different beta values for calculations, I can actually do all of them with beta equals 1, and I have to fix the alpha value to what I want, and I can easily go, I can easily hop around the different beta values as needed for the problem I'm working on. So this can greatly improve our computation times. Now, when we're talking about gamma random variables in R, things still follow the standard conventions of D for density, P for cumulative distribution functions, Q for quantiles, and R for random number generation. So once again, X and Q are quantiles, P are probabilities, N is the number of observations. Now, something about this for the gamma distribution is that rate and scale, I can specify either one. I don't have to specify, I'm not stuck with strictly rate or strictly scale like I am with the exponential distribution in R. So the gamma distribution in R is a little bit more flexible. And so here's an example of the D gamma function. And here's what the plot of the density looks like. You can see that's 0 to the left of 0, and then very small probabilities as I get far to the right. Then we have our cumulative distribution function. We have our quantiles, as always. And then we have our random number generation. And we can see that when I do this, everything is, virtually everything is less than, 4.5. All right, so now for an assignment, what I want you to do, I want you to compute some things about the sum of independent gamma random variables with the same rate but different shapes. And I want you to apply this to the 7th event for exponential random variable independent identically distributed events. That's all I've got for you. Take care and goodbye.